Okay. Here's the plan today. We'll talk about a few more topics for the rest to end the course, and then I'll wrap it up, and then we'll do the exam review after I stop the recording as I promised. Okay. For those of you who come, you definitely get the information at the end. But let's cover something also for the exam. Okay. Just to remind you about, as you see from the Moodle announcement, I'm holding potentially 2 review sessions for you. You can ask any question about the exam after your study. It will be next Monday and next Wednesday. You can see the dates from the Moodle. And just make sure you confirm your attendance. If there are too few confirmations, it may not be worth, I might just collapse the 2 sessions together. Just make sure you confirm your attendance, okay? It's completely just for you. If you don't feel the need, I don't need to hold it, right? Yes? We'll talk about the exam, don't worry, yeah. I'll talk about it at the end. But that session there is only just for you to ask questions. All right, let's continue from where we left off from last time, okay? Let's just review the game that we are trying to play. It's the Tower of Hanoi, okay? Okay, let's just wait a little bit. I think guys are still coming in. All right. The Tower of Hanoi, I assume you know how to play the game. Let's just get an insight very quickly, and then we'll see the Java code, and I'll do some tracing for you. And then we got more topics to cover about this recursion here. You're given like n different disks over here, and then from the largest to the smallest, from bottom to top. So this is a strategy recursively, okay? Basically, you're going to somehow to see every disk except for the last one, okay? Let's say this is P1, pack number 1, this is pack number 2, and pack number 3. So here is the strategy. Recursively, we're going to move this part over here, which is everything except for the last one. We're going to remove that to the intermediate one. The goal is really to move from P1 to P3, everything. What we will do is we'll reduce the problem to something that's strictly smaller, which will be everything except for the last one. Recursively move this particular strictly smaller stack onto the intermediate P2, and then move the largest one to the targets, and then recursively to move that strictly smaller one into the targets. That's kind of the 3 phases we talk about. Okay, let's see one example very quickly. As you can see, the diagram over here is the solution for if you got 3 disks. Let's say we got A, we got B, we got C. Okay, let's say the problem is C is the largest, and then B, and then A. Let's say this is what we want to do. If you want to solve this problem recursively, overall, you're going to see 3 different phases. Let's see the very first. And then, in turn, each phase may also be run recursively. So that's why it's worth studying this particular problem. Let's say for this one here, the problem is we want to move this stack of 3 disks over here from P1 to P3. You can think about the P1 over here is the origin, and the P3 over here is the destination, right? And according to the strategy, we have to somehow move everything except for the last one, the largest one here, right? Everything will be here, just A and B. We want to move A and B to some intermediate pack. So what will be the intermediate pack over here? Since we want to move from P1 to P3, so the intermediate will just be P2, right? So somehow the Java code is going to calculate what the intermediate pack is, okay? So now, this is what you will see. Let's see exactly what we're doing here. So now, you will see that we got phase number 1 over here, the one that's surrounded by the pink. That's strategy phase number 1. And then we have some phase number 2, and then we got phase number 3. Phase number 1, we are basically going to move the top 2 over here from P1 eventually to P2, which is the intermediate, right? That's the result. But how do we do that? We'll just get there in a moment, because itself is also a recursive call, also recursive, until you get to the base cases. So after we have moved the top over here onto the intermediate pack, which is P2, we're going to do the second phase, which will be to move P1, the largest one, from P1 onto P3. That's what we will do, right? After that, we're going to somehow move this into this top stack over here from P2 onto eventually P3. Right? That's the recursive step we have, the 3 phases. Okay? For this particular case. Of course, if you increase the number of disks, if you increase that to 4, to 5, or even to 10, it works the same way. You can always divide the solution into 3 phases. Okay? So now, let's see how we can trace it. Okay? Before I trace it, I want to draw your attention one more time. Okay? Let's focus on this particular first phase over here. Okay? You can see the first phase over here, our goal is to move this particular top stack, which contains A and B, the green and the blue, eventually from P1 to the intermediate P2. Itself is also another problem for the Tower of Hanoi. But now rather than having 3 disks, we only got 2. And now the idea is, in order to move this stack of 2 disks from P1 to P2, now the intermediate pack becomes P3. So that means we can subdivide. You can see the pink over here can be subdivided into 3 phases. This is phase number 1, the orange. Phase number 1, phase number 2, and phase number 3. Okay, that's something you can also, when you trace the code, you will see. One more thing I want to draw your attention to. Okay, if you look at the problem we are trying to solve over here, we are trying to move this stack of 2 disks over here from P1 to P2, right? And now, if you look at the final solution, the orange one, the first phase, in order to achieve this, is going to move the top one again. Now we further reduce the problem from 2 to 1, just 1 disk, the green one. And then, since this is the origin, this is the destination. In this case, what will be the intermediate one? Whatever does remain, which is P3. So that means what we will do is we'll move from P1 to P3, which is intermediate. And then from P3 to P2, which is the destination, right? So you will keep swapping the intermediate packs depending on which subproblem you're solving. Okay, it's a very general account for the problem you're solving. Of course, it's a very general solution that's recursive. You got 3 phases. The first and the last phases will be recursive. Okay? Any questions about this? Yes?
What if all you don't start with all the work on the first call? What if they're all like this one?
Well, you're basically asking what if we start with maybe we only got maybe 2 disks in P1, 1 disk in P2. No, that's not, that's against our assumption. We assume that we always start with one particular pack with a stack and then move eventually to another pack. Okay. Yeah, okay? Like the picture over here, that's just the game, the rule of the game. Okay, now let's have a look at it. Once you understand this particular conceptual idea divided into 3 phases, let's look at the Java code. Again, very quickly. I renamed the parameters a little bit just to avoid confusion, but you can still download the code to make sure it works to your understanding. Again, the main thing is we are trying to define this particular helper method that is recursive. Okay, let's see how we can use it. It's really important. We're assuming that every time when we are using it, we have an array of disks, which will be, in this case, maybe A, B, and C, so of size 3. And when we are trying to call this recursive helper method, this is one particular call over here. Let's try to understand this. What are we doing here? Okay. What we have is we have the disks array called by value, so we don't really create any intermediate new arrays. And then we are saying that we are going from index 0 to index something. In the beginning, simply from the beginning index to last index for the disk. You can think about if these are the 3 disks that we are handling, A, B, and C, right? So we start with from 0 to 3, and then at some point we're going to go from 0 to 2. 0, 1, and 2. 0 to 2 from the beginning, and during the recursion, we might simply go from 1 to 2, and 2 to 2, etc. Okay? Now, what's really important is to understand the last 2 parameters over here, 1 and 3. So that simply means what's the origin and what's the destination. The original problem over here tells us we should move everything from P1, which is 1, onto P3. Okay? In this case, we'll simply pass 1 and 3 over here. But now, every time when you're trying to solve this problem over here, it depends on what the origin is and what the destination is. You can calculate the intermediate one accordingly. Okay? For example, let's say over here, if the origin and destination are 1 and 3, that means the intermediate is simply just 2. Right? On the other hand, if we are moving from P1 to P2, in this case, the intermediate is P3 instead. Right? You will see the calculation. The calculation is simply just use 6 minus the origin and destination, right? If you got 1 and 2 being the origin and destination, the intermediate would just be 3. If you got 1 and 3, it would just be 2, right? It's a little bit trick for the arithmetic over here. Okay, and how do we express the ideas where we simply say we only take the top stack over here, removing the largest one? How do we express that? Let me just go over this. The way to do that is say from and 2 minus 1. Okay, that's the trick. So this will make sure you're solving a strictly smaller problem. You're only handling the top 2, except for the last one. Okay, we'll see the trace in just a moment. Okay, one more thing to say, and also you can see that over here, you can see, let me use a different color here. You can see origin to intermediate, and then from intermediate to destination. So that's exactly corresponding to our strategy, right? So eventually we want to go from origin to destination, but we want to make sure in phase 1 and phase 3, we actually move everything except for the last one, except for the largest one. First of all, from origin to intermediates, and then from intermediate to destination. Okay, just knowing some convention over here. And then what about the base case? The base case is basically where we are only moving a single disk, in which case from index is simply equal to index. For example, so we are simply say from and to are pointing to the same disk. That means we want to move B from some pack to another. So what will be the strategy for that? Well, simply just move it. You don't have to worry about any recursion any further. Okay, and one more thing to say. When you study the code, this is phase number 1, recursive call. This is phase number 3, also recursive call. This is phase number 2. Okay? Now, let me just trace the code very quickly together with you so you get some insight. But I would suggest during the exam period study, you want to study this code very carefully. It does illustrate a very nice pattern for recursion. Okay? Any question about the code before I go on to trace it? Yes? Intermediate over here, yes. You mean what it means or about arithmetic? Yeah, you can think about over here conceptually, we start with a stack of n disks, right? The strategy is, let's say we want to move from P1 over here to P3. So that means the intermediate is simply just P2. We only got 3 packs over there. So now, let's say we have to move everything except for the largest one at the bottom there, recursively from P1 into the intermediate, which is P2. And then move them from P2 to P3 in the third phase. That's the strategy. Okay? Any questions about the code anymore? Any more questions? All right. Let's now see how we can trace it. Okay? When you look at the slides, I got 2 recursion trees for you. This is just one of them, just either horizontal or vertical. Doesn't matter. Let's just go through the horizontal tree together. How do we start with? We start with a call like this. So we're assuming that we only got 3 disks over here. We got A, the smallest one, B, the intermediate one, C, the largest one at the bottom. C, B, and A stack up. And this is how we start with. What we are saying is over here. We simply use the Tower of Hanoi helper, the recursive helper method. And then we pass the reference for the disk call by value. And then we're saying that in the beginning, we want to move A, B, and C from index 0 to index 2. That's what we want to do. Okay? From 0 to 2, we want to move from P1 to P3. Okay? In this case, we know that, very quickly, we know that the intermediate one is simply P2. Intermediate one is P2. Just know that in our mind. So now, when we call this one here, it's basically not the base case yet. So we're going to follow exactly these 3 phases, right? The second one is not a recursion, so we'll see strategy right away. But for the first and third phases, they are recursion. Okay? So you will see that this is the first phase, and this is the last phase. And this is simply just move the largest one which is C, from P1 to P3. So that one's done automatically. But now for phase number 1 and phase number 3, this will depend on some further recursion. Right? Okay, so far so good? Okay? The idea is if you want to move A, B, and C, so A, B has to be moved somehow to the intermediate one, but A, B itself is too large to solve as a base case. So that's why you need recursion. So now, how do we solve this one over here? It's just another recursive call. You can see, let me use a different color here. What about this one here? You can see over here, and also over here. Notice the changes over here. I want you to compare the inputs. You can see over here, we got 0 and 1 versus 0 and 2, right? You can see that we actually discard the largest one, which is C. So now we want to move A and B, in this case, from P1 to P2. And notice that P2 is the intermediate I just talked about, right? Okay? And then eventually, the third phase over here will just be moving also A and B, but now from intermediate one, again, it's intermediate to the targets, right? This is origin, and this is destination. Okay? That's about the phase 1 and 3. Now, phase 1 over here is going to be running some further recursion, because when you talk about moving A and B, we got 2 disks. You only reach the base case if you got only 1 disk at a pack for you to move on. But you got 2. So you need to run some recursion. How do we run recursion? This is exactly this case over here. When you want to move just A and B, only 2 disks. What you would do is you're going to move this guy over here, except for the last one, except for the bottom one, from the origin to the intermediates as the first phase. And then from intermediate to destination as the third phase, right? Again. The same 3 phases. So again, let me just trace one branch for you. You can see that over here, you can see this is phase number 1. Okay, this is phase number 3. Okay, now what's phase number 1? If you think about what we're doing here, if you think about this particular recursion over here, we are going from P1 to P2. What's the intermediate in this case? P3, right? So that means you will see that over here, we'll first of all do from P1 to P3. So now think about, in this case, the intermediate is actually P3. That is why you will see P3 over here from the origin to the intermediates, and then from the intermediate to the destination, right? You can see the intermediate keeps changing among the recursive call. That is why when you see the Java code, we simply just do a simple arithmetic. Depending on what the origin is, which can be P1, P2, or P3, also, depending on what the destination is, also can be P1, P2, or P3. You calculate what should be the intermediate one by using this simple equation here. Okay? And now, if you look at this one particularly, let's use green over here. If you look at this one here, we're basically done. Because when you look at that, when you say the indices over here, 0 and 0, it's basically reaching the case where we got from is equal to 2. That means we're considering just a single disk. How do you move a single disk? Well, just move it. So you don't have to worry about any further recursion. In that case, we'll simply do 0 and 0. So that's why, for example, you see we are going to move A, which from index 0 to index 0, you can see the original array, index 0 to index 0 over here. Okay, from P1 to P3, and then etc. You will see this case over here is also a base case. Imagine that if I give you, let's say, A, B, C, D rather than A, B, and C. That means 1 more disk. You can imagine that we're going to follow exactly the same solution pattern. We always got phase 1, phase 2, and phase 3. But if we got 4 disks, that means we got further recursion to call in order to reach the base case. Okay? Again, this example here is not so easy to grasp just by listening to the lecture. I try my best to illustrate to you, but I do encourage you to look at the code, maybe with your colleagues, or just come to me. All right? Any questions about this before I move on? Okay, now, the next, since we now know how it works, and that's the Java code, here's the next question, which is also important for your exam. When you are given a recursive method, how do we know how efficient it is? Let's say for this particular one, how do you calculate its running time? In order to calculate its running time, there are 2 steps you have to follow. Number 1, given the Java code that is recursive, you have to formulate the code into some recurrence relation. That's step number 1. And then step number 2, once you formulate the recurrence relation, you somehow have to solve it. And in 3101, a later course, you're going to learn about a more systematic way, some formula called the master method. But for this course, we just give you, once you formulate the recurrence relation, you can simply just observe how the recurrence relation will be unfolded, and things will be quite straightforward. Okay, I'll do 2 examples with you today. One will be Tower of Hanoi, and the other one will be binary search. Okay. Let's do this one here. Step number 1. Given this code over here, how do you formulate the code into this particular recurrence relation? Okay? Recurrence relation simply means it's going to be a set of equations over there. You got base cases, also you got recursive case. Okay? As we know, the base case is over here. This is the base case. Okay? This is the base case. And the else part over here is the recursive case. Okay, that's a recursive case, right? Base and recursive. Now, how do we formulate them? You can think in this way over here. When we talk about the base case, when from is exactly equal to 2, that means we're considering just a single disk. Agree? Just a single one. It's a single disk, one disk. Okay, and then over here, this is the more general case. We can think about we're considering just n disks, just any n that is larger than 1. And then in the case of one disk, based on what we learned about asymptotic upper bounds, right? You can see that this one here is simply just printing something without any further recursion. So it's a constant operation, right? So that is why you will see, first of all, the base case, you got t, this t is just a normal symbol for running time, just time. The running time for this particular Tower of Hanoi recursive helper, when the input is simply just one disk, and the running time will just be 1, which means it's constant. Okay? Any question about the base case? You might get more than one base case sometimes. We'll see example. Okay? You might get more than one, but typically you just get 1 or 2. Okay, that's a base case. And then what about the recursive case? The recursive case basically is saying that when we got n disks over here, how do we call the recursion? If you look at the recursion, especially when we got 2 minus 1, conceptually, this is what we're doing. When you are given, let's say, a stack like this, okay? Let's say we got n disks. How do we call the recursion? We're going to basically just call the recursion on everything except for the bottom disk, in which case, this will be the n minus 1 disks, right? That's a strategy, right? And that will be the recursion to solve for first phase and third phase, okay? Just make sure you understand that. So that means over here, you can think about over here, 2 helper over here, this one over here is on n minus 1 disks because we simply got 2 minus 1, right? Just considering one disk strictly less, okay? Except for the last one. And then we got another recursive call, which is considering the same size of the disk, right? Also n minus 1. So this is also n minus 1 disks. And what about the middle phase over here, the second one? The second phase, let me just highlight it. The second phase is basically like this. Again, it's like a print statement. Simply move the single disk from one pack to another. That will be just constant. Okay? So that is why we can simply say each phase, each of the recursive phase over here, start over here and start over here, they are simply just t of n minus 1. We're reducing the problem size to n minus 1 disks rather than n. And then we're doing that 2 times. And then plus 1, which is the second phase over here, right? That's the formulation. Okay, any question about this? Of course, we only go by example in the class. You might be given something maybe not as complicated as the Tower of Hanoi, but what you really make sure is, before the exam, you might be given something different, simpler, but you should know how to formulate the recurrence relation. Okay. Guys, any question about this for the recurrence relation? Especially going from the code over here to the recurrence relation here, which consists of the base case and the recursive case. Yes? Yeah, well, if in the exam we only ask you to say, now look at the code and tell us the running time, and then just you don't have to justify. You can just do whatever you like. However, we may just simply ask you part A for the question, now formulate the code into a recurrence relation, and that is something you will have to do. And second, we say once you formulate the recurrence relation, now solve it, which I'm going to show you. Okay. I would say the one we're going to give to you to the exam will be no more complicated than this, no more. maybe most likely simpler than this, but we just have to know the complicated ones. Okay, yeah. Okay, let's see how we can solve this. Basically, there's only one strategy you can follow. Basically, unfold the recurrence relation until you can see the pattern. Okay, let's do it together. Okay, you will also get the details on the slide, but I'll just do a few steps with you so we can get a feel about how it can be unfolded. Okay, so now let me just clean this part over here, and then we'll solve it together. Okay. Okay, let's see for here. What we will do is we'll start with the general case. Let's say I'm given just Tn. Okay, by definition of the recursive case, right? We start with Tn. That would simply be just 2 times T of n minus 1 plus 1. Okay, just first step, just copy that. Now, how do we unfold? Basically, what I need to do is to apply the definition. Let me just use a different color. I want to somehow unfold this particular one. So now you can see the n over here, rather than n, is going to be n minus 1. And I know that by applying this particular equation over here, is what's that going to be? 2 times t over here, 2 times, yep, t, and then n minus 1 itself minus 1, right? N minus 2, and then plus 1. Okay, and then I can say the original one is simply like this. Are you okay with the first step? That's the most crucial part. Make sure you know how to apply the definition. Yes?
How did you get n minus 2? Sorry.
No problem. How do I get n minus 2? That's the most crucial part, actually. So think about this. If you look at that, if this is n minus 1 over here, right? And we are trying to apply this particular definition, we simply substitute n by n minus 1. That means rather than n minus 1, it would be n minus 1 minus 1. Guys, you okay with this, right? Okay? Basically, if you get this first step, all you got to do is unfold one more time, and then to see how we can reach the base case. Let's do one more time. And now, let's say how we can do that. Let's say I use pink over here. How do I unfold this one particularly? So that would be 2 times t, and then n minus 2 minus 1, right? It'd be n minus 3 plus 1, and then I will simply get everything else also into the context, and then we can talk. Are we okay? Basically, up to now, it should give you enough hints, but I will get there. Okay? So now, what we want to do is as follows. We want to say this unfolding will just keep going until we can reach the base case, which is over here. Okay? What I really want to reach is something like this. I want to reach basically t n minus 1 over here. Let's just now, and now, how should be the surrounding part for this t, oh, sorry, not t n minus 1, beg your pardon. What I meant to write is t1. Eventually, I want to reach t1. Because once I reach the t1, I know no more unfolding can be conducted, right? That will be the terminating case. But now, what would be the surrounding for t1, right? As you can see, somehow, so far, if you're not convinced, you can definitely do more unfolding. We started with 2 times and then plus 1. And then we got 2 times, plus 1, right? Here we got 2 times, 2 times, 2 times, and plus 1, right? And I think I should get one more plus 1, I believe, over here. Okay? And also plus 1 over here, right? That's kind of the idea. So now, what we want to know is, if I got something like that, that means I should really get eventually 2 times, right? Something like that. And then plus 1, and plus 1. It's like a pattern like that. Now, how many 2 times do we have in this case? That's the question. I heard n. N is good enough, I can tell you. But to be more precise, why would that be? I tell you a trick over here. You just gotta make observation. Over here, you can see that in the case where it is minus 2, we got 2 here, we got 2 here, right? When in the case we got minus 3 over here, we got 3 here, and we got 3 terms over here. So now, T1 is as if we say n minus 1. Don't you agree? Okay, that means we should get exactly how many times 2? N minus 1. n minus 1 times. And also, we got how many 1s do we have? Also, n minus 1. So eventually, what we will get is 2 to the power of n minus 1 plus n minus 1. Let me just recap very quickly, okay? I'm going a little bit rushed, but it's not really rocket science over here. Hopefully you can see the pattern over here. We started with this Tn over here. We just do one, just copy the rule from the recursive case. And then we try to unfold the first time, unfold Tn minus 1, and then unfold Tn minus 2, and then unfold Tn minus 3, and so on, until we can get to the case where it simply does T1. And now by observing the surroundings, that's something you will get. So now, what would be the big O for that? If this is the equation we got. 2 to the power n, right? Good. So this is exactly big O of 2 to the power of n. I would say if you simply miss this to say 2 to the power of n, it's okay. It wouldn't be so disastrous. It's still almost correct. Yes? So you mean over there? Yeah, T1, you can definitely put 1 there as well. Yes, I see your point. If you want to be very precise, you can definitely say T1 will also be reduced to 1. So that means, to be more precise, it should be just n. You're right, but it wouldn't really matter, right? Because it's just a lower term, right? The idea is you want to unfold so that you can observe the pattern to see how it can gradually unfold until you get to the base case, and then observe the surroundings. Guys, are we okay with this? Again, 2 things you should know. Number 1, given the Java code, formulate the recurrence relation, which consists of base case and also recursive case. And number 2, once you get recurrence relation, solve it. And the way we solve it is going to be just the same for the exam, just observing the pattern, and it should be okay. Let's do one more exercise, okay? You can study this, and if you want to ask me during the review session, you're welcome to, okay? Yeah. Sure. You can see that, let me say, the question really is about this one over here, right? Yeah, basically, let me just write this down. We want to eventually reach T1 over here, right? Would you agree that 1 over here is just equal to n minus 1? Yeah. Agree, right? The reason I need that is because I want to figure out exactly how many 2 times and how many plus 1 I have. If you look at the very first term, if I only say minus 1, in that case, I got one time of two times, and 1 turn of plus 1. If I got the second one, which is n minus 2, in that case, I got 2 turns over here and 2 turns over here. I'm just counting. I want to get to the point like how we did in math. Yeah. Of course, up to this point, it's not programming anymore. It's just about doing some math. Okay, let's do one more example over here. What about binary search, which we did last time, right? Binary search. For the binary search, you can see that over there. If you look at the recurrence relation there, again, step number 1, you may not be given the recurrence relation right away. So how do we get from here to here? That's step number 1. How do we formulate it? You want to first of all see how many base cases you have. Okay? In this case, we got one base case over here. This is empty array. Right? You can see base case number 1 as we talk about base case. And base case number 2, this is simply just one element array, right? And then we also got a recursive case. So that means the recurrence relation should really consist of 3 equations. So for the case where we only got 0 elements in the array, it's going to be just 1 because we just return false. It's constant. In the case where we got only 1 element in the array, so that means T1 over here, we got only 1 because we simply return this particular array indexing and some comparison. It's also constant. Whenever it's constant, you can just put 1. So what's so good about the 2 base cases? Okay? So the idea is once we figure out a recursive case, we want to unfold it until we can get to the point to reach the base case. Let's see how the recursive case can look like. The recursive case, if you recall how the binary search work, you're basically going to, first of all, calculate the middle position. That one there is just constant operation. I'll just put big O of 1. And then you can go either to the left or to the right. Notice that we are not adding up the work from the left and the right, either way. You don't really go both ways. So that means you can either go for this way here, in which case we are trying to do a recursion, and where this is just telling us go to the left half of the array, which is only of size n over 2. And then you can also go to the right half, in which case it will also be of size n over 2. So either way, not both. So this is how we can formulate this particular relation here. So if you look at that over here, so Tn, which means over here, if you look at that, n over 2, which means we can either go to left or we can go to right. And the plus 1 over here is exactly how we calculate the middle position calculation. Are we okay with this? Guys, I can pause a little bit if you got questions. Make sure you got step number 1 sorted out, and then we'll solve it. This one here, if you compare with the previous one, we're given some different Java code. You just have to know whenever you're trying to solve the recursion, how is the problem size being reduced? In the case of the previous one, if you look at that, in the case of the previous one, since we are doing 2 minus 1 and 2 minus 1, that means the problem size is only reduced by 1. Okay? On the other hand, for binary search, we're basically going for the middle. So that means we're truncating the search space by half. That's why you see n over 2. Okay? Any questions before I go on to solve it together with you? Okay? I presume you're okay. So now how do we solve it? Okay? Again, let's try. We start with Tn over here, and then the recursive case is like this. So Tn over 2 plus 1. Let's do the unfolding. How do we do it? Let's say over here, how do we unfold T and minus 2? Okay? Now, give it a try. How do we unfold T and over 2?
You plug in n minus 1 over there for the value you choose.
Okay, you're saying that we have to somehow plug in a value over here for n, right? I agree. But what value should we plug in? Exactly, if you said n minus 1, that's not the case, right? So what we should do is we should plug in a number over here for n over 2. So what we will have is we're going to have t n over 4, agree? Because plus 1, of course. But I'm just saying, make sure you're comfortable with this. So n over 2 is going to plug in for n over 2 divided by 2, n over 4, right? And after that, we're going to have something like this, n plus 1. Are we okay with this? It seems to be a little bit simpler in this case, which is okay, right? Just a different recurrence relation. Let's do one more. How do I plug in now n by n minus n over 4? So what I would do is I will try to unfold this one over here. So what would that be? So now n would be basically n over 4. n over 4 over 2, n over 8. Agree? So what I will get is I'll get t of n over 8 over here plus 1. And then I will get a blue back plus 1. And then over here plus 1. Are we good? So now, again, what's the big picture? We want to keep doing this unfolding until we reach the base case, which can be either 1 or 0. Let's make the assumption, okay? Let's make the assumption that you will also see on the slides. Let's assume the following. Let's see the value of n is simply just 2 to the power of something, I. Just make it easy. So n can be 64, n can be 1024, okay? Now, that's maybe also a big hint for you, okay? So what we want to do is to say, keep doing this until we can reach, let's say, T1, until we can reach that. So now the question is, once we get there, what should be the surrounding? A series of plus 1, agree? But let's see how we can figure that out, okay? Now, if you look at that, in this case over here, you can think about this first one here, 2 to the power of 1. We only got 1 plus 1, only one term for the plus 1. In this case, it's 2 to the power of 2. We got plus 1, we got plus 1. It seems like the exponent for 2 correspond to how many plus 1 we should have. Agree? Now, if we got to here, how many plus 1 should we have? How many? Because I said that you can assume n would be just 2 to the power of something, right? Would you agree? N would be, for any, n would be 2 to the power of log n. Okay, for example, you can say 1024 is equal to 2 to the power of log 1024, right? Log 1024 in the base of 2 will be 10. 2 to the power of 10, just go back to the number. Okay, it's just a math. Now, so now this will be exactly just log n. And then T1 over here, it will just be 1. So we got 1 plus log n. And what should be the asymptotic upper bound for that? Log n. That's a lower term. Drop it. So you got big O of log n. Okay, that's what you have. Guys, any questions? Yes. Which one? N equals, which one? Oh yeah, I'm just saying that assume that n is simply a number that you can take the log of 2, of base 2 with an integer. For example, n could be, for example, 4, it can be 8, it can be 1024. When you take the log on base 2, it just gives you an integer. Yeah, we'll just assume that. Not really divisible by 2 is different. It's actually quite different. It's actually a stronger assertion we are making. We're saying that when you take log of base 2 of this particular n, it will give you an integer. Yeah. Of course, you can simply say it's bound. It can just be the ceiling of log n, but let's not get there. Okay. Guys, are we okay with this? I would say study these two very carefully. One is the binary search. The other one is the Tower of Hanoi. Maybe try, how would you calculate a recurrence relation for reverse of? You know, things like that. Give it a try and see what answer you will get. Questions before I move on about running time? We okay? Yes? You know what? This part will be recorded so you don't have to take a photo. Yeah. Maybe you haven't come to this class so far, so we actually always record. All right. We always record, right? Yes. Except for today, for the exam tips. Right. All right. Right. Guys, any questions about this? Yes, go ahead.
Will you be posting this slide?
Definitely. I'm just saying that the exam tips would not be posted. That's my point. Yeah. Don't worry, this will be posted. Yeah, of course. Don't panic. I'm going to post the lecture for sure. Yes. Huh? The login part? Okay. Guys, please. Okay. Okay, login part, you mean how we get to this part? Okay. Thinking this way. You can think about we are basically starting with n over 2, right? Each time we unfold, we're going to, think about n over 2 to the power of 1 for the first time, right? And then we get to n divided by 2 to the power of 2. And then eventually, we want to get to some part over here such that n divided by 2 to the power of something is going to give us 1. By definition for log, that's exactly the log you will get. That's why. Basically, we want to calculate exactly how many times we have to go from n down to 1. You will see something very similar when we talk about Mergesort today, which I keep promising. I will definitely talk about it today, Mergesort. All right? Alrighty. Now, that's about the running time, and I would like to talk about another topic also to do with recursion, which is about how we can prove the correctness of recursion. Okay? Let's do one simple example together, and the pattern you have to follow will be just similar for all questions you might be given in the exam. Okay? So let's say this is a problem we are given. Okay? We are very familiar with allPositive over here, right? So we want to calculate to see if all the numbers inside this particular array is positive. Okay? What we do is we simply call some recursive helper method here, starting from 0 until a.length minus 1, right? That's the array we're talking about. And then this is the definition for the recursive helper method. Remember, we got two base cases, right? So this is the case where from is strictly larger than 2, that's empty array. And this is an array of single elements. So these are the two base cases. And then we also got this else part, which is the array is too large for us to handle right away. That's why we have to call the recursion with from plus 1. Okay, we okay with this? Now, how do we prove that this is correct? It's incredibly straightforward. The answer is you have to prove by mathematical induction. And that's why I want to summarize the idea to you at this point, and then in the slide you got complete details. Okay? Let's just get the idea. If you want to prove by mathematical induction, you have to prove, in this case, in the case of array, we have to prove first of all base cases. So we got base case number 1, base case number 2. So for base case number 1, we simply talk about an empty array, in which case from is simply larger than 2, so just empty array you can think about. Okay? And for the second case, it would be an array of size 1, because from is equal to 2. That means we're only considering just one element. So for these two cases, we can prove right away. You just plug in the exact value for the base cases and see if your program returns the correct value, and that's it. Now, what about the recursive case? All you got to do is you have to make an assumption about the recursive call to say, I assume this recursion is going to give me the correct result. And then using that correct result, I can figure out a solution for a bigger problem. Okay? So now, thinking this way, something you learned about in the math course, something called inductive hypothesis, right? So now, conceptually, this is what you have to do. What I do is, I'm going to assume for this particular part of the array, starting from over here, from plus 1 until 2, that's exactly the range of indices for this particular recursive call, right? Okay, that's something I assume. I simply assume with no reservation, it's just going to be right. Which means if I try to call this particular recursion here, it's going to tell me the green part, the array, the green part over here, whether or not all the elements are positive. Okay? Now, how do I know the original problem, which is simply just from? You can think about the original problem I'm trying to solve is basically like this, the pink part. It's basically an array that is strictly larger with just one more elements over there. So now the idea is, since we make the inductive hypothesis over here, we assume the result that's returned from the recursion over here is going to be correct. It tells us whether or not all the elements in the green part is actually positive. And then we combine that result, which is either be true or false, together with whether or not this particular element is true or false, is positive or not. And then combine them together using conjunction. Over here, it's going to give us the right result. Okay? That's the overall picture for proving the correctness. Again, you got to prove the base cases, number 1. And once you prove the base cases, you have to make an inductive hypothesis. Okay? In this case, the green part, which is from the indices from plus 1 until 2, the green part. And then eventually what you want to prove is the pink part, which has got one more element, strictly larger. Okay? I'm going to use that to prove. That's only the big picture, but we're going to see the proof altogether. Okay? Are we okay with this? So you got 3 cases to worry about. Okay? One more thing to mention, you can see that over here, this is the recursive helper method we are calling, and notice what we are calling that on. We're calling that the from index start with 0, which is the minimum index that's possible for array A. And A.length minus 1 is the maximum index that's possible for that, right? Just notice that. We're going to use that for the proof. Any questions about the concept over here? You're going to see exactly this roadmap over here. Okay? Now, what we will do is let's use some slideshow over here to show you the same code over here. Base case number 1. Okay, we're going to use mathematical induction, and then base case number 1. In the case of empty array over here, we know that for empty array, since you cannot find any violation for all positive, so it should be simply just true. Okay, and our program prints exactly true. So that's how we prove the base case. All you got to do is justify to say for empty array, what should we return? And point to the program to say which line does return that correct result. That's how we prove it. Okay, line 3. You can see line 3 over here, we do return true for the empty array. Okay. Now, what about base case number 2? Base case number 2 is about an array containing only one element, in which case it depends on what that single element, whether that's positive or not. In that case, we can point to line number 4, in which case it does return whether or not that particular element is larger than 0 or not, right? That's base cases, okay? Base cases are usually very easy to prove, okay? Now, for the recursive case, what you need to do, number 1, you have to make it an inductive hypothesis, which means before I can make the argument about an array of size n, I want to make a hypothesis on array of size n minus 1, basically, okay? Now, how do I do that? Number 1, inductive cases. Let's make the inductive hypothesis. Now you can see that I'm saying that for this particular recursive helper method, if I'm calling on A, and then you can see the from part over here is from plus 1 until 2, right? That's exactly the green part I'm talking about over here, just that. I'm not including the from over here, I'm not including that, only making the assumption on the green part. Okay, that's what I'm doing here. And then I'm saying that it will, I'm just assuming the following. This recursive call will only return true if all the numbers are positive, otherwise it returns false. That's my assumption. You don't need to prove it because that's an assumption. And now we're going to make this assumption over here to grow the size of the array, to say the following. Given that this part is assumed to be correct, we want to prove the way the program combines the green part and also some extra element, the pink part over here, the way they combine that is simply just correct. Okay? But how do we argue that? Okay, you will see this, the proof in the slides. So now, when we got an array, let's say from to 2, right? So that's basically the array like here. Thinking this way. So we got from over here, this is from, and this is 2. When we have this entire array to actually cover, all the numbers will be positive if the following is the case. This subarray, all the elements over there are positive. Not only that, this element alone should also be positive, right? However, this part over here has been done by the inductive hypothesis using the recursion. So all we got to do is calculate this part here, and then using this recursion result based on the inductive hypothesis and combining them using conjunction. That's all we got to do. And now, if you look back over there, that's exactly what's set in the proof. Okay, the first element A from will be positive, which is the pink one over here, the pink one over here, and also second one, starting from plus 1, from plus 2 until the 2, which is the green part over here. They're all positive. Okay, and then eventually we can say that by the inductive hypothesis, that's also important. Because now, the second part over here, without this inductive hypothesis, it cannot be assumed. That's why you got to say that. Okay? Say that over here, and then you will say the way you combine them is corresponding to exactly line number 5. Okay? Okay, line number 5. Make sure always when you do the proof, you got to explain something mathematically and say that this is the corresponding line to look at in the code. Okay? That's why I keep referring to the line number over there. Okay? Okay, so finally, this is also important. All we just have proved was basically only the method from line number 2 to line number 5. It's only the helper method we are proving. But we want to prove that the all positive, which only has the original array, that one's correct. So how do you got to say one more thing? You want to say, given any from and any 2 is going to be correct. Now, given that, in this case, we're calling this particular helper method here with the beginning index being 0 and the ending index being the maximum index for A. So that one is going to guarantee to cover every element in that particular array. So it's going to be correct. It's a very fast walkthrough for the proof for you. But I would say whatever you do for the exam, it'll be very similar. Of course, it'll be a different problem. Okay, questions? You're asking about from plus 2? It's part of the inductive hypothesis because you can see over here, you can see that over here, all positive, right? It's being from plus 1, which is basically the green one over here, right? You can, so from plus 1 is exactly over here. This is from plus 1, basically just after from. We're talking about this particular range over here. When it becomes from plus 2, as you can see, it's part of the inductive hypothesis. It's simply just covered by that. You stay with from plus 2. You will change. No, actually, thinking this way, what we're doing is we're saying that all positive helper, when you pass just from plus 1, there's an absolute value for that, right? We're saying that from this particular index, which is from plus 1, until the index 2, for this range of the elements in the array is going to be calculated properly by the method, right? Yeah? What if you have more than one recursive case? It will be done in a very similar way. You can see that over here, for this particular example, we only got one recursive call. That's why we only have to make one recursive inductive hypothesis. If you got 2, of course, you make 2 hypotheses, right? Yeah. Okay, questions about this? Questions? What you can try is maybe try to do the some of the question we did previously for the recursion. Try to prove that and then show your proof to me. I can give you some feedback. Okay? All right. Are we ready for the final topic? All right, merge sort. So now, this is what I would do. I think very likely that you're going to talk about merge sort maybe again in 2011. So I want to give you some intuition quickly and show you the code. And then talk about running time. That's what I would do. Hopefully I can do all these in 10 minutes. Okay? How do you understand merge sort? Conceptually, it's extremely easy. Very easy. Let's say this. If I want to sort an array like this, just like that, okay? And the array can be out of order or can be already sorted, doesn't matter. You don't make any assumption about the array. There are two phases. Conceptually, there are two phases for the merge sort. First of all, it's called split. We want to split the original array into 2 subarrays. One is called left, the other one is called right. Okay? So what we will do is I will split that, and the split itself is very cheap operation. You just split. Okay? Now you can think about what we're doing is you can think about this is the first half, and this is the second half. Once you split, you simply got this, and then you simply got that. Oops. Okay, just split. That's the first phase. And what happened after you split? After you've split, you call the sort recursively. And then what you would do is you would say sort. So this is the recursive call. I want to sort just this strictly smaller instances, 2 instances. I will sort. So once I sort, what does that mean? That means these elements after the split are simply unsorted. But now I'm going to sort them recursively. So once I get them, I'm going to have just another array that is completely of the same size, and also another array over here. And I'm going to use green to tell you they are completely sorted. And now, I don't have the answer just yet, because I got 2 sorted arrays, rather than a single one. That's where the merge sort name comes from. We're going to merge them. And you are doing this actually for lab number 7, if you know what I'm talking about, right? I hope. Now, once I got this one over here, what I should do is to have one more stage. And then I'm going to merge these 2 sorted arrays, and then I'll simply just merge them. And that complete a merge sort. Conceptually, it's very easy. Okay? When you see the code, it's not too bad. I will tell you what you really have to pay attention to implement correctly is how you merge 2 sorted arrays. That's the part. Okay? Let's have a look at that together. So that's the merge sort. I'll also make a source code available to you. So for your interest, I'm actually, rather than using a primitive array, I'm using array list. So you will see array list over here. Okay? Now, I want to give a high-level view. For the details, I will leave it up to you. Okay? Now, let's just have some idea over here. Basically, over here, this is just the iterative version of your lab number 7 part of it, not a recursive version. Okay? But for the lab 7, I just want you to practice to solve problem recursively. But to solve this iteratively, for the code over here, basically we got two, for merge sort. So over here we're given two lists over here. We got left and also we got right, assuming that both of them are sorted. For example, left is simply this particular array, 24, 45, 63, 85. And right is simply 17, 31, 50, 96. They individually are sorted, but you cannot just combine them using concatenation. It's not possible, right? So I want to somehow combine them, merge them. Here's the idea. We're going to keep two loop counters, I and j, for the two lists, okay? So we got I over here, the pink counter, and also we got j over here. Initially, I and j will just be 0. I will just do a few iterations with you together, okay? Now, initially, we're going to combine, basically every time you're going to look at what's the value for L at position I, and also what's the value for R at position j. Initially, it's 24 versus 17. So we know that 17 should be put into the merge array, right? In that case, I'll put 17 into it. But now I need to update the counter. Because 17 has been copied over, conceptually, this value is gone. What I should do is, rather than j pointing to here, j is now going to point to over here. When you study the code, it's going to correspond to exactly this branch of the code over here. We're going to do j++. When the value of R, j, is actually less than or equal to the value for Li. Okay? And then let's do one more. So now, how do we compare the value for Li versus Rj? Well, it's going to be 31 versus 24. Now, what should we put? 24. So we put 24 over here. So conceptually, this value is gone. So now what we should do is we should really move the I by one position. That's exactly the I++. You will see that, right? You can see this is what we have to do every time for the loop. We keep doing this. What you will get is eventually you will get a sorted list. Okay, you got 17, 24, you got 31, 45, 50, 63, 96, also 85, and then 96, eventually. It's a sorted array. So this, I would say, this code is iterative. It's not recursive. It's just a helper routine, helper method for the merge sort. Okay? Make sure you understand the merge. Itself is not recursive. Now, assuming that the merge is working, so I just did a very quick illustration for you. Now, how do we define the merge sort? Let's say we're defining this particular sort method here, and we're taking just a list of integer. Okay? Now we're going to following exactly the process I just mentioned. Split, recursively sort the two halves, and then merge the two sorted halves. So how do we do that? So now you can see that, well, first, if this list is simply just empty, you don't need to sort anything, just empty list. If the list is of size 1, then we can simply just return the value, the list directly. Now, what about a recursive case? Now, let's see how these phases will work out. Okay, let's see very quickly. So what we'll do is, first of all, we see where the middle index is, like how we did for binary search. Find the middle part, and then we're going to create two lists over here, left and right. Over here, just do a sublist from the API. The sublist doesn't really create a new list. It's simply just do some aggregation to it. Okay, that's some implementation detail. The left is simply from 0 to middle, and then from middle to list.size. Okay, that's exactly how we divide into these two halves. And then after that, this is where the recursion happened, right? Sorted left is simply just recursively called sort on the left. Sorted right is simply recursively called sort on the right, right? Two recursive call. And now, once we get sorted left and sorted right, what should we do? We merge them. How do we merge them? You simply call the merge, which we just defined over here, merge them together, after which we simply return the sorted list. Conceptually, it's not difficult, but I'm going to trace one instance of the code for you. Okay? Any questions about the code here? I think the merge part may be a little bit more complicated than the recursion itself. For the recursion, you just have to understand what's the big picture of sorting, for which you can just refer to the recording afterwards. Okay, I'll be quick. So now let's do some tracing very quickly over here. I thought about doing the whole thing, but I'll just do some parts, okay? So now what we will do is, what's going to happen is we're going to split this into two parts. So this is the first part, the left, and this is the right. Let's see exactly what's going to happen, okay? So what we're going to do is, first of all, we're going to split. Okay, split. What we will get is we're going to split that into 85, 24, 63, and 45, right? Exactly this list. No sorting just yet. And then recursively, we are going to sort this part, split this part here, right? And also, this will be the second part, right? So that will give us basically 85 and 24, right? Now, how do we split them? We want to split them until we reach the base case, basically. And then for that one, we'll again get 85, and also we get 24. And now what we get is now 85 and 24. So we got one list of size 1, another list of size 1 as well. Now what do? We want to make sure this is already the base case. So we just return this list directly. And we also return this list directly. So now what we should do is we want to merge them. Okay? When we try to merge them over here, what we will get is something like this. When we try to merge these two, merge 85 with 24, what we get is we get 24 followed by 85, right? So it's going to replace 24 and then 85. Okay, and now we can continue with this part of the recursion, right? You're going to get, again, for this one split, you get 63 and then 45, and then you get 63, you get 45. So that's the splitting process. Now, when you actually go to the second stage, you get 63 and 45, and now you will merge them. When you merge them, what you will get is you get 45 followed by 63. And now you're going to replace them back. So you got 45 over here, and then you get 63. No, 45, yeah, and then 60, yeah, we're going to merge them again. Yeah, exactly. So now, finally, we're going to merge these two lists over here. So what we will get is we'll get 24, and then 45, and then 63, and then 85. So only this part is sorted. Okay? And one more tree to trace over here for this part here. That's what we will get. Okay, once you get it, merge the two lists together. That's how you get it sorted. Yeah? How you prove the merge sort correctly is something similar. You also assume when I actually call the recursion on the sort on the left and the right, individually they will give me sorted list. And when I merge them together, I can assume the merge actually works, so you will give me the sorted list. Something like that. Okay. All right? Okay, final account. So what should be the running time for this? I will just do that very informally with you. Remember, what's the running time for selection sort and insertion sort? Quadratic, n squared. It turns out, if you look at how we lay out the tree, this is, by the way, something you will learn in 2011, so I don't want to say too much. The running time depends on how many times you have to split your original list all the way down to when you only got one element list. That's basically what you have to do. And now, like how we did for binary search, if you start with a list of size n, how many times do you have to split? Each time you just go from n to n divided by 2, and then n divided by 4, and then all the way to only size 1. How many times do you have to split? Log n, right? It turns out you have to do log n splits. Okay, that's only about the number of splits. What about after each individual split? Once we actually get the element back from over here, we had to merge them, right? Merge is the expensive part. Okay? It turns out you can see that over here, we are merging over here in the top level. We are merging two lists of size n over 2. Over here, we are merging two lists of size n over 4, and etc. Oh, actually, n over 8. Okay? Informally. Right? So now, just summarize by one particular picture over here. Okay? If you think about this, is basically how you start with. You start with a list of size n. Okay? Eventually, you want to do so many splits so that you only got one element list at the bottom over here. We know that you need about log n base 2, log n splits. And now for individual, let's say if I want to merge two lists of size n over 2, it's big O simply just n. Okay? If you want to merge also the list of size n over 4, it's also big O of n. So you got big O of n for each level over here. So for each level, you got n, and how many levels do you have? You got log n splits. So that's n log n. Okay, yes, go ahead. I would say this is like upper bound, which means if you start with a list, let's say with a million, right, it's only going to take a log 2 base, a million splits. That's required. Right? Yeah, so merge sort is actually quite an efficient sort. If you go to arrays.sort in Java API, it's actually how they implement the arrays.sort, merge sort. So it's n log n. So it's good to know how to implement that. Okay, that's the last topic for this course. Should I wrap up in 1 minute and then we'll talk about exam? Okay, actually before the exam, something important, but we'll get there. Okay, let's now go to wrap up the course. Okay, so I just gave you a summary of all the topics that you have learned so far in the course. We learned about exceptions. You know, I'm not going to read them out, but you can go over them. I would say data structures is really a topic we haven't covered so much. You will learn them next semester, 2011. Okay, and then I would say for your, since this is more like a advanced OOP course, so I would say, well, whatever we cover about inheritance, I would suggest that's the part you want to focus more, not just for the exam. That's really something you want to understand thoroughly before you actually go for your workplace. Especially the way I covered, I'm quite confident is quite nice, I would say. The only thing I really wish I could cover but I couldn't is something called generics. I wish I could cover that. However, I do make the slides available to you. It's optional. It's not covered in the exam. But for your learning, feel free to go over the slide. It's completely self-contained. If you understand inheritance properly from my lecture, you should be able to follow that. Come to me for help if you need clarification on the slides. Again, it's optional. You can go there, click on the link, you will see the slides. Okay, also learn about JUnits, etc. Okay, now let me make a very quick recommendation for you. So when you go beyond this course, I would say don't really abandon Java during the break, right? Maybe for many other third-year courses or second-year courses, you don't necessarily learn Java. I would say keep the technique over there. So I got two suggestions for you. Well, I should recommend some book. It's a book that you anyway might just purchase in 3101, the algorithm course. I would say the good thing about the book, they explain each data structure algorithm in a mathematical way, and they only give you so-called pseudocode. It's not written in any programming language. So what can be useful for that? You can just go data structure by data structure, algorithm by algorithm, and then simply just try to program by yourself using Java. Okay, and then guess what? You should also write test cases in JUnits. I think that's the best way for you to practice programming. That's my #1 suggestion. But the book has more than 1,000 pages. It's not possible to finish that during the Christmas break. I'm talking more about long-term investment. All right. Second book is more about OOP. So there is it's a reference book for 3311, the software design course later. But that book over there also shows you very nice object-oriented structure, a little bit like a lab number 6 that we did. Lab number 6 we did is something called observer pattern. But you can also go over the book and try to translate the pattern there into Java. That can also be a nice exercise for you. Okay. Well, if you're interested in software design, you can go to my page. I also have some recordings for them. But again, it's not important. All right, finally, make sure you don't abandon Java and make everything we cover in this course is assumed in 2011 next semester. All right, if you got any problem, get in touch. Any questions? All right, let me stop the recording over here.